lecture. He's a full professor at the EPFL in Lausanne, and he's the head of the Laboratory for Data Security. And I had the pleasure to get to know him in the Global Alliance for Genomics and Health, where he's also active in the field of data security. He has been contributing to privacy protection and laying the foundations on the technological level with quite recent and well-known publications. And he has been pioneering the areas of privacy and security in mobile wireless networks, and also moving into personalized health since a while ago. He is further an academic director of the Center for Digital Trust. And until December 2021, he had led the now concluded Data Protection in Personalized Health project that has been funded by the ETH Council. I would like to emphasize that he is a fellow both of the Institute of Electrical and Electronics Engineers and the ACM, and he has also received recent awards for papers from this association. And I would like to let you know that he's among the most cited researchers in privacy protection and in information security. As you all know, information security is very important for GHH, for federated infrastructures, and we are very much looking forward to your talk. The floor is yours. Thank you.
Very well, thanks, Virginia, for the kind introduction, and thanks for having me here. I assume I have to share screen again, yeah?
Yes.
Which I'm happy to do. Voila, here we go. Okay, so I slightly changed the title to make it more precise, but the topic is unchanged. Let me explain in a few words how we started our journey on this topic. You see here the map of Switzerland, and we started with the challenge of having to see how it would be possible for 3 different university hospitals to collaborate without transferring their data. So is it possible to gather intelligence without transferring the data containing the let's say information about patients? So this being on the side of exploration of the data, so exploring the cohorts, building the cohorts, and then on the side of the analysis. And you see here examples of questions of each of those. And this was carried out in the framework of something called the SPHN, the Swiss Personalized Health Network. And I know that in Germany, you have actually similar initiatives. Now, if we look at the privacy technology landscape, there are a number of items here. And as Fusina pointed out, so I'm a computer scientist, I'm not a bioinformatician. And as we know, there is quite a let's say, cultural gap between the 2 communities. Yet over the last, I would say 6 or 7 years, I trained myself to talk with bioinformaticians, and I think I've now more or less understood their mindset. So coming to this kind of, to see this kind of the problems we have mentioned before, to ask computer scientists immediately says, okay, let's make use of tools, of the appropriate tools. And these tools are, security and privacy tools, notably the encryption techniques, be it symmetric or asymmetric, and then more advanced techniques such as homomorphic encryption or secure multi-party computation. I'm going to say a bit more about that. And then underpinning this is a federated learning, which by itself is not a privacy tool, but is plays an important role in this landscape. And then additional tools are mentioned here on the right-hand side that I put here for completeness, but that I'm not going to address directly. So about the privacy enhancing technology is something that a topic that is going to become more and more popular and widespread in the years to come in bioinformatics, but also in many other fields. So I want you to get a precise idea of what this means and what kind of features they can provide. So let me take one example of the privacy enhancing technology, or PETs, which is secure multi-party computation. So assume there are 5 parties. Each of them possesses a piece of data, say an input, right? So X1, let's call this X1 to X5, if you have there are 5 parties. And they want to make a computation of this data without any of them revealing their own input to any of the other parties. So what we want to see is that there is a protocol that is unfolding, right? And at the end of the protocol, each of them has the output that it is allowed to obtain. We call Y1 to Y5. So for this, let's take a very concrete example. Assume that of these 5 parties are willing to compute their aggregated wealth. So in which case, the input X1 to X5, which in general can represent a scalar or a vector, a matrix, any kind of input, in this case is just a scalar that represents the wealth of any of those, right? So a first attempt, let me just show you the naive way to do this, is that one of them is going to extract at random, to generate a very large number, and then compute the sum of this very large number. This number is meant to be much larger than the wealth of any of these, let's say, stakeholders. Compute the sum and sends it to the next one, who does the same, right? And so each of the wealth are added. It comes back to the original stakeholder or player. And so this individual will receive as a consequence something that is M5, a value M5, which contains the value which is equal to the sum of all the wealth plus the random number. Then it will subtract this value. So it will compute M5 minus R and will provide the outcome to everyone, right? And in this way, each of them knows what is the aggregate wealth without any of them having the possibility to learn the contribution of any of the other ones, and without also having any of them, without, let's say, making use of a trusted third party. Right? Now, this, let's say, somewhat naive solution can work, but it has weaknesses. For example, if the first and the third player collude, they can easily actually isolate the contribution of the second player, just by computing, in this case, the difference between these two values, right? The difference between M2 and M1 will essentially lead to get to know X2. Right. So we show that actually the solutions have to be somewhat more robust, and today's pets actually are mathematically proven to have the appropriate characteristics and properties. So this is for secure multi-party computation. And another example is homomorphic encryption. Homomorphic encryption is that if you take is a kind of encryption such that if you take two operands, A and B, if you encrypt them, each of them, and then make a computation on the encrypted value, you obtain something. If you take now the two operands non-encrypted, so you take the clear text value, you compute something, some function on it, and you encrypt this function. If it is the case that going by one way or the other way, you obtain the same result, this means that you have homomorphic encryption. And this enables the possibility to compute on the data without seeing the data. And this clearly opens tremendous opportunities for let's say, for the kind of problem that is at hand. Now, there exists already a certain number of libraries that achieve this, but we have developed our own in order to be able to do floating point operations at, let's say, with high performance. And so we have developed, let's say, library called Latigo. It's called Latigo because it's lattice-based crypto, which is the underpin, if you wish, a kind of technique that is on which it is used, developed in the Go language, right? And so this library is actually completely open source, and you can find it at the GitHub lab, that the GitHub link that is mentioned here. So once we have these tools, we can do the following thing. We can have the following scenario in which there is a researcher who is willing to define a task. For example, training a neural network model based on data that is in silos, right? Say, for example, in 3 hospitals or let's say 3 institutions where, let's say, patient data are available, including genomic data, right? So the way this is going to happen is there is first the definition of the task, so step number 1. Step number 2, each of the data providers, DP, data provider, performs several training iterations on its own data, right? And then there is a global iteration that leverages on each of the partial contributions. So this is the collective iteration. And at the end, after the training, the model is kept secret for oblivious predictions, or, if allowed, is made public if it is compliant with the policy. So we have already developed and deployed solutions of this kind 2.5 years ago between the 3 institutions I mentioned previously, so between Geneva, Lausanne, and Bern University hospitals. And the application here was melanoma. So we have worked a lot with the oncologists on this topic. And then more recently, we published in Nature Communications the full and more elaborate story in collaboration with the Lausanne University Hospital, but also colleagues at the MIT and the Broad Institute. So what we have done essentially is the following. We have reused already existing publication that appeared in 2019 in Nature Genetics, where the authors, Samstein et al., what they have done was to make 2 more mutational load predictions, survival after immunotherapy, right, across multiple cancer types. And so what we have on the left-hand side, you see here the plot of the original paper as it was published in Nature Genetics in 2019. So we reused the same data set. We split it in 3 subsets to simulate, if you wish, a kind of distributed processing, so data that would be in silos. And we have shown that we can obtain exactly the same results as the ones that have been obtained in clear text centrally. So in other words, without loss of accuracy, it is possible to obtain the same results while keeping the data in silos and by making use of the techniques that I mentioned previously, which means a combination of secure multi-party computation and homomorphic encryption. And as you can see here, from then we also increased the number of data providers. The runtime, in order to achieve this, in order to compute this, let's say, survival curves, actually is a matter of a few seconds. So it's very fast. Then we made use also of this in the case of genome-wide association studies. And again, same approach. So we reused an already existing paper that had been published in 2015 in the Proceedings of National Academy of Science. So the original plot here is in A, so where you see the Manhattan plot with the usual chromosomes and the p-values. And so what we've shown is that we were able to obtain the same results with the data, in spite of the data being split in different silos. So for example, 3 silos, we were able to obtain exactly the same values of the p-values. Whereas if one does not do this, or if one keeps the approaches separate by a meta-analysis over an independent approach, the results can be very disappointing. We also show that it's possible to have with a slight loss in terms of precision or accuracy. It was also possible to do computations with something which is called a fast GWAS, FAMHE, so Federated Analytics of Multi-Party Homomorphic Encryption, fast GWAS, that actually simplifies a bit the computations with let's say very minimal loss in terms of accuracy. So then this is in this field, as we know, what is crucial is to obtain approval from the authorities. So in GDPR parlance, one has to write something called the DPIA, Data Protection Impact Assessment. Sorry for the mishap on with the slide. And what this means, it means essentially to identify what is the situation before you deploy your tools and what is the situation after in terms of threats, threat likelihood, threat impact, blah, blah, blah. So this is actually not a colorful table like this. It is produced. It is a thick, somewhat boring document, but very, very important one. So situation before and then situation after. And as you can guess, red is not good and green is good. And so we have shown all the improvements that were brought by this kind of approach in terms of mitigating, you know, the data leak of vis-a-vis the host or the cloud, the collisions and the collusion that might happen, the corrupted malicious host or cloud, and so on. So this is something that we sent. We sent this document to our authorities in Bern and obtained feedback from the Federal Data Protection and Information Commissioner a bit more than a year ago, who in legal parlance expressed the fact that his office was happy with the approach and encouraged us to move on with the deployment. And as we are even more federal than Germany, to talk with our cantonal data protection authorities. So, which we have done in the meantime, so the thing has moved on. And then we have also applied this also to to several other cases. Let me mention one here, single cell analysis, where, and this actually slide depicts the different stages through which one has to go. In step number one, this is a setup phase. It's about the key generation. It's more the crypto part. And then there is a global model initialization with the appropriate weights that are provided in order to generate the corresponding neural network. Then there is local computation, as very similar to what we have seen for the previous case, to compute the various gradients. And then there is aggregation and global model update. And then after enough iterations, so the iterations, one goes back from step 4 to step 2. And then finally, the secret model is provided in order to support oblivious prediction in such a way that then people can make use of this model with additional data. And actually, this work was done in collaboration with Manfred Claassen of Tübingen. In some cases, also the model can be decrypted, but this is really a matter of policy. Voilà. Then, okay, the second slide about this topic. So this is how the whole pipeline is organized. We take the patient samples, and then there is pre-processing. Multi-cell inputs are provided, and then there's the computation of the convolution. Then there is pooling, and then computation of the dense layer, and finally the output in terms of you know, whatever, let's say, prediction can be made based on these data. And so what we have shown, what this slide shows here, is the accuracy that can be obtained. So on the so what is provided here is for two different actually let's say on the left hand side is for the phenotype classification, and on the right hand side for the multi-cell classification. What you see here is that if we take the left hand side, the accuracy is, let's say, the same as with let's say centralized data in clear text, whereas if the data is done, let's say, purely locally without exploiting, let's say, all the data, then the accuracy drops quite dramatically. The same phenomenon can be observed on the right-hand side. So, okay, so here is Manfred's testimonial on this, who, let's say, this was really multidisciplinary in the sense that he helped us a lot with this single cell analysis, understand exactly what this was about, and we took care of the deployment of the tools and running the whole thing on with our, let's say, technology. Okay, so based on all this, so we came to the conclusion after a while that there was so much traction on these techniques that an academic lab could not, let's say, provide support to end users. So we said, well, we'll have to find a solution, and that would essentially, the solution was consisted in saying, let's set up a kind of a commercial entity, so which means a company, also based on the fact that we had come to the conclusion that this kind of technique was useful not only in the case of medical data, but also in other application verticals. And so this came to the creation of TuneInsight, and Juan Troncoso Pastoriza is actually the CEO of this company, and I'm working part-time now in this company. So the idea is to industrialize what we have just seen, that, and based on the fact that there are these three main trends. So there's data dependence, and the data play a role that is growing and growing year after year. There is regulatory pressure, because there is more and more awareness of the need to protect the data, because people, I mean, no privacy, no freedom, right? So I think that everyone has understood how crucial it is to do these things so properly. And the number three is, unfortunately, the growing relevance of cyber risks, right? So what the company provides is very much aligned to what I've shown previously. So assume here there are four entities, and so each of these entities will essentially run software provided by TuneInsight, and then the federated confidential computing will be carried out on the related data. So, which means that without this kind of approach, well, one has to move the raw data to a centralized location. Whereas with TuneInsight, it is possible actually to minimize the transfers, and the work is done on aggregated and encrypted data. All the computations are carried out over encrypted data. So this, with this tool and with this company, then it was possible to expand. And so now we have kind of nationwide, almost nationwide coverage from Geneva to Basel and Zurich that support the kind of question that we have seen before, and also of course, more sophisticated questions. And here's a customer's testimonial from Professor Olivier Michelin, who is the head of the Precision Oncology Center here at the Lausanne University Hospital, who essentially expresses his satisfaction about this technique. And after some years, we have learned how to talk with oncologists who are very different from computer scientists, but of course they play a very important role. And then we have really found a common language for the appropriate deployment of these kind of tools. And this is another actually customer, user, Alex Leisley, who is at Inselspital, who is actually in charge of a project called the Swiss BioRef that is defining, let's say, reference values for patients. Now, as I hinted before, the technique that I've mentioned is applicable across verticals. So first, and of course, most prominent example so far for us are hospitals and pharma, so really apply it to medical data. But this can also be used in insurance. And we have worked on this with a company, with Zurich-based Swiss Re, a global company providing reinsurance capabilities or services, and then also cyber intelligence. So in the case of cyber intelligence, it was same idea. Data about cyber attacks are actually sensitive because they can reveal vulnerabilities, and therefore organizations are unwilling to share this data, but they are willing nevertheless to establish, to extract intelligence from the various, let's say, from organizations that are, let's say, exposed to similar risks. And so we have an ongoing collaboration on this topic with Arma Suisse, or the research arm of the Swiss military. Now, before my conclusion slide, I would like to emphasize, let's say, to summarize the landscape in this field of share without sharing. So because also to facilitate the comparison with other solutions that you will probably hear about or have already heard about. So if we start here, we start from the big blue bubble. There are two options initially. Either you say, okay, let me protect the whole thing, my computations, by hardware. So which means I'm going to make use of specialized processors, and the data will be sent through a secured pipe, so a la HTTPS, to this secure processor, and this secure processor will decrypt, make the computations in clear text, encrypt the outcome, and send it wherever it has to be sent, which works well, relatively well in terms of performance. However, has the immense drawback that one has to trust. One has to trust the CPU doing this, right? And it turns out that there have been a number of side channel attacks against these processors, which shows that actually they are more fragile than was initially hoped by their promoters. So as a consequence, this may be considered a kind of a short-term patch, but is not really satisfactory. More satisfactory are solutions that are based on software. One solution is in software is just to do vanilla federated learning, meaning, okay, let's do computations at each of the data providers, and we get some partial results, some aggregated partial results, and we will work on them in clear text in order to find the combined result. But actually, a number of papers have shown that this is not appropriate, because these partial results can actually leak information about the patient data, and therefore this should not be done, right? It is actually happening here and there, but this is not satisfactory and is not state of the art. So consequently, one has to say, no, we need to protect partial aggregates. Now, to protect partial aggregates, one solution is to add some noise, right? And this is basically where differential privacy is used. Put some noise on the partial aggregates in such a way that they reveal less about the data, the patient data, for example, in this case, on which they have been built. But adding noise means deliberately reducing the accuracy of the results. So this is clearly not satisfactory. Therefore, the other solution, which is much cleaner, but a bit more sophisticated, is to protect the partial aggregates by crypto. And here are two options again. Either protect by homomorphic encryption or protect by secure multi-party computation. Computing only by homomorphic encryption, that is not scalable in terms of number of parties you can involve. This scales up to 2 or maybe 3 partners, but it's not going to bring you further than that. So homomorphic encryption alone is not okay. Secure multi-party computation alone is also not okay, because experience shows that then the amount of data that you have to push around among the different data providers becomes completely overwhelming. You have to push terabytes of data, and then performance collapses. Consequently, the correct solution consists in combining the two, homomorphic encryption and secure multi-party computation, and the combination of the two is called multi-party homomorphic encryption, and this is what exactly what QNinsight does. And this is a solution that's been we have essentially finalized in the company, and that we've developed, and then after many benchmarks come to the conclusion this was actually the way to go. Okay, let me conclude. So what we have done is that we have streamlined the solution to the problem of privacy preserving federated analytics, and we are happy to report that this works on one of the most demanding benchmarks worldwide, which are Swiss university hospitals. Don't forget that when you are outside of Switzerland, you think of Switzerland being a country. As soon as you are within Switzerland, actually you see a constellation of cantons. And each hospital reports not to the federal government, it reports to the cantonal authorities, right? So in a way, Switzerland can be perceived as a kind of mini international benchmark, right? So we have deployed the tools to achieve this goal, so to be really able to do exploration and analysis on cohorts, on data that are scattered, provided, of course, that the data have been homogenized and the quality of the data is there. These are, of course, prerequisites that have to be fulfilled. And we believe this to open unprecedented opportunities for privacy-conscious data collaborations, because this makes the game symmetric again, right? Instead of, if you have two collaborating entities, A and B, and A would like to know the data of B, B wants to know the data of A. So, but A is unwilling to send to B, B is unwilling to send to A, and so on. So there's a kind of Zugzwang situation or deadlock that is essentially problematic, and therefore we believe that the solution that makes the whole game symmetric has also the virtue of being a kind of an encouragement to fueling the collaboration, and will facilitate essentially carrying out collaborations at scale. Okay, and I think I will close here, und ich würde gerne auch Fragen auf Deutsch willkommen. Ich kann das probieren, wenn Sie wollen. And thank you very much für Ihre Aufmerksamkeit. Thank you.
Yes, thank you very much for the very interesting talk. And I think that we can immediately open the floor for questions.